Hello everyone. I'm going to present our paper, Camp in the Odyssey, Proofly Robust Reinforcement Learning with Certified Radius Maximization. This work investigates how to improve the certified robustness of deep reinforcement learning agents. The authors are from CSIRO's Data 61, the Cybersecurity Cooperative Research Center of Australia, Deakin University, and the University of Chicago. I will begin by introducing the background and the motivation of our work. As we all know, DRL agents are applied in various high-stakes domains. However, these agents can be attacked by introducing perturbations to their observations of the environment. An attacker can add perturbation to the observation of an agent, and the policy of the agent may recommend a wrong action under this attack. In the real world, this can lead to serious or even fatal consequences. Against this backdrop, several lines of research aim to provide provable robustness guarantees for DRL agents. One such approach is policy smoothing. It is a certification method that offers a global lower bound on the expected return of the agent. The method is straightforward. At each time step, a Gaussian noise is added to the observed state, and we will have a randomized state action trajectory for the episode. By repeatedly running the episode and collecting these randomized trajectories, we can then apply an adaptive version of Neyman-Pearson lemma to certify a lower bound on the probability that their return exceed a given threshold. From these, we can also compute a lower bound on the expected return of the randomized trajectories. However, there is a clear trade-off between the certified expected return and the certified radius. For example, as shown in the figure on the right side, when the certified radius increases, the certified expected return may drop sharply. A steeper trade-off usually indicates that the agent is less robust and therefore not ready for deployment in real-world scenarios. What makes things more complicated is that in existing certification method, the certified radius is determined through binary search or other numerical methods. This makes it impossible to determine how the certified robustness of the agent can be further optimized. Therefore, the core research question we address in this paper is that how can we further optimize the certified radius by leveraging correlated variables of it? So now let's move on to the method we proposed in our paper. First, we came up with a loss function called CAMP to improve the certified robustness of DRL agents. To get there, we go through 3 steps. Step 1 is to reformulate the certified radius by change of variables. The constant certified radius is formulated to a function of the policy pi, a new variable psi, and a sampled return value. Next, we derive a surrogate function that is positively correlated with the formulated certified radius. Finally, we break the surrogate function down into a per-step local radius, which is tied to a statistic we call the Q-value gap. The Q-value gap is just the difference between the top 1 Q-value and the runner-up from an oracle Q network. And here's the key. The certified radius actually increases as this gap gets larger. So that's where the camp loss comes in. If the agent picks the correct action, we just push this Q-value gap wider. But here's the thing. You cannot just drop the camp loss directly into a DLL training loss if that training paradigm is directly modeling the Q value. So instead, we propose policy imitation as our training setup to make camp work. I will explain why we do this and how it works. For example, Q value probably is the most challenging case for applying camp because it directly models the Q value by a Q network. It works by minimizing a temporal difference loss. In each time step, the Q value predicted by the network for the current state action pair is pushed toward a target Q value. But the Q value can be overestimated, and this has been a known issue for more than a decade. Studies have shown that when the Q value is overestimated, the training often converges to a policy that is not optimal. So if you think back to the camp loss, you will notice something. When we increase the Q value gap, camp can actually push the Q value itself higher. And this can cause problems because it may lead to unstable training or even prevent the model from converging. So our solution is to use policy imitation as the training paradigm. We first train a reference policy in the normal way, following the Q-learning paradigm to model the oracle policy. Next, our primary policy learns to imitate the action of this reference policy, but importantly, it does not try to copy its Q values. So specifically, we compute the cross-entropy loss between the normalized Q value vectors from the primary and reference policy networks. This loss encourages the primary policy to align its action with those recommended by the reference network, but it does not directly replicate the reference network's Q values. With this policy imitation loss in place, we can now safely add the camp loss during training because the primary policy is no longer directly modeling the Q values. So we can avoid the instability issue. Next, let's dive into the experiments we ran to evaluate camp. We evaluated camp in 6 environments, 3 classic control tasks, and 3 Atari games. We compare camp to 2 baselines in terms of both certified robustness and empirical robustness. The first baseline injects Gaussian noise from the same Gaussian distribution used for certification into the observations of the agent during training. On the other hand, the second baseline, named noisy net, randomizes the weights of the linear layers in the Q network to aid efficient exploration during training and improve return obtained during tests. So first, based on the certification results across 6 environments, we can see that camp significantly improved the certified robustness of the agent compared to both Gaussian and noisy net, especially on the classic control tasks. Next, we also measure the empirical episodic robustness of the agent in a deterministic environment. So we use PGD attack to manipulate the agent's observation. So given a fixed perturbation budget, the attacker perturbs the observation at each step until the policy takes the target adversarial action, or if the total budget is exhausted. Any unused budget carries over to the next step, and the attack repeats. According to the results, we can see that the agents trained by CAMP are more robust than the baselines in this setting. While the gains appear smaller on Atari games, it is worth noting that the agents in these environments are already highly robust against the PGD attack. Next, we also evaluate the agents against a stronger auto-PGD attack. Auto-PGD can achieve its goal with smaller per-step perturbations, which allows it to sustain the attack over more steps. And based on the results, we observe that the camp agents remain more robust than the baselines, even under this auto-PGD attack. So to wrap up my talk, in this paper, we propose CAMP and the policy imitation to enhance the certified robustness of DRL agents. They come with several advantages. First, they provide clear and explainable improvements in certified robustness of DRL agents. Second, they deliver significant gains in both certified and empirical robustness, especially in classic control tasks. Finally, the framework is scalable to environments with large discrete action spaces. However, there are some limitations as well. First, this method currently applies only to agents operating in discrete action spaces. Second, the improvements on Atari games are less pronounced. Finally, this approach may introduce additional training overhead. So regarding these limitations, we aim to address them in our future work. Thank you for your attention. Please feel free to contact me via email or by scanning the QR code on the screen. If you have any questions or if you are interested in future collaborations.